Welcome class to the Stat 215 Lecture 7 video. During this lecture, we are going to go over the following 5 objectives. First, we are going to define the joint probability mass function of discrete random variables x and y. Second, we will define the joint density function of the continuous random variables x and y. Third, we are going to define marginal distribution. Fourth, we will define the conditional distribution of random variable y given x equal to x. And fifth, we will define statistical independence of random variables x and y. Let's get started. So just to take a look at joint probability distributions, the PMF and PDF problems we have seen so far were restricted to one-dimensional sample spaces, meaning we were focused on a single random sample rather than 2 or more. Now, consider the simultaneous outcomes of more than one random variable. Let's take a look at an example. If an 18-wheeler is to have its tires serviced, X represents the number of miles the tires have been driven, and Y represents the number of tires that have to be replaced. What is the probability that the tires are used over 30,000 miles and the truck needs to have 5 tires replaced? This type of example is going to motivate this section. Let's start with our first objective, to define the joint probability mass function of discrete random variables x and y. So for our discrete case, f of x comma y is a joint PMF of discrete random variables x and y if f of x comma y is greater than or equal to 0 for all x comma y, the summation of f of x comma y over y and x equals 1, and third, the probability of x equals to x comma y equals to y equals f of x comma y. For any region A in the plane xy, the probability of x comma y belongs in A is equal to the double summation over A of f of x comma y. Now that we've looked at the theory, let's start looking at an example. Suppose 2 ballpoint pens are selected at random from a box that contains 3 blue pens, 2 red pens, and 3 green pens. Let x equal the number of blue pens selected. Let y equal the number of red pens selected. We are now going to try to find the joint PMF f of x comma y. So, if we think about this logically, the possible values of x comma y are 0, 0, 0, 1, 1, 0, 1, 1, 0, 2, or 2, 0, where, say, 0, 1 means that no blue pens were selected, 1 red pen was selected, and then by default, that meant also 1 green pen was chosen, although we're not interested in what happens with green pens, at least not at this time. So, continuing with our example, how many total ways to pick any 2 pens from our 8? This sounds like a problem we've had to solve before. So we're going to look at 8, choose 2. Using our combination formula, we know that that's 8 factorial over 2 factorial multiplied by 8 minus 2, or 6 factorial. This is going to be equivalent to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 6 times 5 times 4 times 3 times 2 times 1. We're going to cross this out. That will leave 8 times 7 over 2 times 1, which will equal 28. So the answer to how many total ways to pick any two pens from the 8 is 28. Next, how many ways to pick X blue pens and Y red pens? Well, we know that there are 3 blue pens, 2 red pens, and 3 green pens. We'll let X be our number of blue pens that are selected, Y be the number of red pens that are selected, and since we're only selecting 2 pens, it'll be 2 minus X minus Y to leave us with the remaining pens selected. At this point, we're going to have to leave things as they are. We can't solve for X and Y at this time. We'll get there later. Now, we want to write our joint PMF. Bright news is the previous slide gave us all the parts we needed. So our joint PMF is going to be f of x comma y equal to the number of ways to pick X pens and Y red pens, or 3 choose X multiplied by 2 choose Y multiplied by 3 choose 2 minus X minus Y all over our total number of ways of having 8 pens and selecting 2, or in other words, 28. If we'd like to look at the probabilities in a chart, we can definitely do so here. Notice we have our different possibilities for our blue pens and our red pens and their corresponding probabilities. We also have our row totals and our common totals. These are going to be what we call marginal totals later in this lecture. And then, of course, our grand total should be equal to 1. Let's keep going. Now we want to find the probability of x comma y belonging to A, where A is the region of x comma y given that x plus y is less than or equal to 1. Okay, so let's take a second to think about this. X plus y less than or equal to 1. That means that we have to be strictly talking about the events where either both x and y are 0, just y is 1 and x is 0, or just x is 1 and y is 0. Therefore, our probability of x plus y being less than or equal to 1 is going to be f of 0, 0 plus f of 0, 1 plus f of 1, 0. We can use our chart to find these probabilities. So f of 0, 0, that's going to be 3 28ths. 0, 1. 3 14ths. And since we're here, 1 0 is going to be 9 28ths. We will add up our probabilities to get 18 28ths, or 9 14ths. There we go. That's the end of this example problem. Now let's take a look at objective 2. To find the joint density function of continuous random variables x and y. Okay, so the joint density function for our continuous case. F of x comma y is a joint density function of 2 continuous random variables x and y if f of x comma y is greater than or equal to 0 for all x comma y. The double integration from negative infinity to infinity of f of x comma y dx dy is equal to 0. and the probability of x comma y belongs to A, where the double integral over A of f of x comma y dx dy for any region A in the xy plane. So not bad. Let's do a quick example. Whoops, sorry, jumped ahead of myself. Let's look at this information first. So the integral from a to b of f of x dx is the area under the curve f of x between a and b. The double integral with the inner integral being from c to d of f of x comma y dx and the outer integral being from a to b for dy is the volume of the space under the surface f of x comma y in the region such that a is less than x less than b and c is less than y less than d. Now let's take a look at an example. A local bank serves customers in the lobby and at the drive-thru. On a randomly selected day, let x be the proportion of time there is at least one customer at the drive-thru, and let y be the proportion of time there is at least one customer in the lobby. Suppose the joint density function is f of x comma y equals 2/5 times the quantity 2x plus 3y on the bound 0 less than or equal to x less than or equal to 1, comma 0 less than or equal to y less than or equal to 1, and 0 otherwise. To start off, we want to show that the double integral from negative infinity to infinity of f of x comma y dx dy equals 1. Okay, no problem. So to start off, let's plug in our upper and lower bounds. So using our example, we know that x and y are on the bounds from 0 to 1. Plugging in our function of 2/5 times the quantity 2x plus 3y and quantity dx dy. All right, very good. Now we can begin integrating. If you don't remember, when we do a double integral, we start with the integral on the inside and work our way out. So this is going to be equivalent to 2/5 multiplied by the integral from 0 to 1 of x squared plus 3xy from 0 to 1 dy, which is equivalent to 2/5 times the integral from 0 to 1 of 1 plus 3y dy, which is equivalent to 2/5 multiplied by y plus 3y squared over 2 from 0 to 1, which will be equivalent to 2/5 multiplied by 1 plus 3/2, which will equal 2/5 multiplied by 5/2, which equals 1. Perfect. Looks good. We've successfully shown that our double integral is equal to 1. Let's continue on with our example. Now we'd like to find the probability the drive-thru is occupied between 0% and 5% of the time, and the lobby is occupied between 25% and 50% of the time. Okay, so my own personal choice, I like to make the bounds of my integrals fractions. You could have also made them decimals. So to start off, we will go 1/4 to 1/2 and 0 to 1/2. Same function as before, if my hand doesn't add extra marks. So we'll have 2/5 multiplied by the quantity 2x plus 3y dx dy. Now it is a simple matter of solving for our probabilities now that we have our problem set up. So to start off with, I'm going to pull that 2/5 out. We have our integral from 1/4 to 1/2. Start by integrating the inner integral, so that will become 2x plus 3xy from 0 to 1/2. Close bracket dy. Once we simplify, we will have 2/5 multiplied by our integral 1/4 to 1/2 of 1/4 plus 3y over 2 dy. Make sure to check my math. Make sure I haven't made a mistake. But looking at it, looks good. Okay, next up, solving our outer integral. So 2/5 multiplied by y over 4 plus 3y squared over 4 from 1/4 to 1/2. This is going to be equal to 2/5 multiplied by 1/8 plus 3/16 minus 1/16 minus 3/64. Yes, that looks right. All right, to make this a little bit easier on myself, I'm going to change this so that we all have the same denominator. So we're going to have 2/5 multiplied by 8/64 plus 12/64 minus 4/64 minus 3/64. This is going to be equal to 2/5 multiplied by 13/64. Simplify along our diagonals, and that will give us 13 over 160. Yes, looks good. So the probability that the drive-through is occupied between 0 and 50% of the time, and the lobby is occupied between 50% of the time, is 13 over 160. Wow, good job. Now, that brings us to the end of our second objective. Let's talk about our third objective, the marginal distribution. We're going to look at this in both the discrete and the continuous case. Marginal distributions. Given a joint density function, or joint PMF, f of x comma y, for random variables x and y, how do you find the individual PDFs, or PMFs, g of x and h of y? G of x and h of y are called the marginal distributions. We can find these in the margins of the table for our joint PMF. I kind of already alluded to this earlier. So, for h of y, it can be found on the row totals. The column totals contain our g of x. Let's properly define it. The marginal distributions of x alone and of y alone are g of x equal to the summation over y of f of x comma y, and h of y equals the summation over x f of x comma y for the discrete case. And g of x equals the integral from -infinity to infinity of f of x comma y dy, and h of y equals the integral from -infinity to infinity of f of x comma y dx for our continuous case. Let's take a look at our third example. So, if we are curious of g of y in our discrete case, that will be each of our f of y's where x is equal to, our f of y's, our f of x comma y's, where x equals 0, which we can see is going to be 3/8 plus 3/14 plus 1/28, which equals 5/14. For h of 1, that's going to be our f of x comma y case where y equals 1. So in this case, we have our y equals 1, which means we would add 3/4 plus 3/14 plus 0, which would equal 3/7. It's pretty easy in the discrete case. Let's take a look at it a little bit further. So our marginal distribution of x. One way to write this would be into a chart where we have our values of x and their corresponding marginal distribution probabilities. In other words, 5/14, 5/28, and 3/28. Remember, we are finding these values right here. And in similar fashion, we can find our h of y in our column totals. So our marginal distribution of y, we have our various y values and our marginal probabilities. Still doing okay? Now let's take a look at our continuous case. For this example I should say, let f of x comma y equal 2/5 times the quantity 2x plus 3y on the bounds from 0 to 1 for both x and y. Let's try to find our marginal distribution g of x. So, for g of x, we are going to integrate from 0 to 1 of our function 2/5 times the quantity 2x plus 3y dy. Remember, when we are trying to find g of x, we must integrate over y. This will equal 2/5 times the quantity 2xy plus 3y squared over 2 from 0 to 1. This will equal 2/5 multiplied by the quantity 2x plus 3/2, which we can simplify to be 4x plus 3 all over 5. To properly write this out, we will say that g of x equals 4x plus 3 all over 5 on the bounds from 0 less than x less than y and 0 otherwise. Now at this point, that brings us to the end of marginal distributions and the beginning of conditional distributions. You'll see that these topics have a connection. Let's take a look. Conditional distributions. Let us recall that the probability of b given a equals the probability of a and b over the probability of a for when the probability of a is greater than 0. Now, let a and b be the events defined by x equals x and y equals y respectively. Then, the probability of y equals y given x equals x equals the probability of x equals x comma y equals y over the probability of x equals x, which we can simplify to f of x comma y over g of x for g of x greater than 0. So now you can see that for conditional distributions, it is our PMF or PDF over our marginal distribution. Let's look further. So for two random variables, x and y, the conditional distribution of random variable y given that x equals x is f of y given x equals f of x comma y over g of x for g of x greater than 0. And in similar fashion, the conditional distribution of x given that y equals y is f of x given y equals f of x comma y over h of y for h of y greater than 0. Let's take a look at our first example. This will take a look at the discrete case. So once again, we're still going to use the same table that we've been using throughout this lecture. And we'd like to find the conditional distribution of x given y equals 1. In other words, we want to find f of x given 1. So, using our formula, f of x given 1 is going to equal f of x comma 1 over h of 1. H of 1, if we remember, is going to be the summation of x equals 0 to 2 of f of x comma 1. This will be 3 fourteenths, I did that the first time too, plus 3 fourteenths plus 0, which will equal 3 sevenths. Let's go back and review that. So remember, we're looking at h of 1. So when y is 1, we are looking at this row, the 3 fourteenths plus 3 fourteenths plus 0, which equals our 3 sevenths. Got to use our marginal distributions. Okay, so that part was review. Now let's take a look at the next part. So that means for f of 0 given y, we will have f of 0 comma y over our marginal distribution of 3 sevenths, which would equal 7/3 multiplied by f of 0 comma 1. If we scroll up, f of 0 comma 1 we can see that is 3 fourteenths. So 7/3 times 3 fourteenths gives us 1/2. Next, we want to find f of 1 given 1, which would equal f of 1 comma 1 over 3 sevenths. Once again, flip the fraction and multiply. We need to find f of 1 comma 1, which is going to be 3 fourteenths. Once again, same fraction we multiplied before, that's going to equal 1/2. Last but not least, we have f of 2 given 1, which is equivalent to f of 2 comma 1 over 3 sevenths. Flip our fraction and multiply. We need to find f of 2 comma 1, which is equal to 0. And as we know, anything multiplies by 0 just equals 0. Very good. So, now, our conditional distribution of x given y equal 1 is the probability distribution of the number of blue pens chosen, given that exactly 1 red pen is chosen. So for us, there are 3 blue pens and 3 green pens left from which there is to choose 1 more pen. And it's the following of what we just calculated. Here is our table of results. Not too bad, right? Let's take a look at the continuous case. Example 6. Let x be the unit temperature change and y be the proportion of spectrum shift that a certain atomic particle produces. The joint density is f of x comma y equals 10xy squared for when 0 is less than x, less than y, less than 1. 0 otherwise. First thing we're going to be asked is to find the marginal density g of x. Okay, no problem. So g of x is going to be the integral from x to 1 of 10xy squared dy. Let's pause for a minute and double check our work. So we want our marginal density for g of x, which means we need to integrate over y. And our bounds are going to be from x to 1. And our function, again, 10xy squared. Okay, everything looks good. Now, we just need to integrate. So this will become 10xy cubed over 3 from x to 1, which will equal 10x over 3 minus 10x to the 4th over 3. Let's simplify that a little bit, and we will have 10/3 x multiplied by the quantity 1 minus x cubed on the bounds of 0 less than x less than 1. All right, very good. Let's move on to the next part of this example. My guess is you probably know what's coming. We're now going to try to find the conditional density f of y given x. So for f of y given x, we have the formula f of x comma y over g of x. F of x comma y was given to us in not the previous slide, but the one before that, slide 29, which will be 10xy squared. Next, we need g of x. Lucky for us, we calculated it in our previous slide, slide 30, which is 10 over 3 x multiplied by the quantity 1 minus x cubed. If we simplify, we will get 3y squared over 1 minus x cubed on the bounds from 0 less than x less than y less than 1. Perfect. That brings us to the end of that part. Let's keep going. Now we would like to find the probability that the proportion of spectrum shift is more than 1/2 given that the temperature increased by 1/4 unit. Okay, so what we're being asked to find is the probability of 1/2 less than y less than 1 comma x equals 1/4. Let me read that again just to make sure we got it all right. We are asked to find the probability that the proportion of spectrum shift is more than 1/2 given that the temperature increased by 1¼ unit. Okay, so let's calculate. So for us, we're going to integrate from 1/2 to 1 of our function f of y given x equals 1/4 dy. Remember, this is given that the temperature is increased by 1/4 unit. Now we must integrate. Whoops, nope, getting ahead of myself. First, we need to plug in for our function. So, still integrating from 1/2 to 1, we will have 3y squared over 1 minus 1/4 over, 1/4 to the 3rd dy. Where am I getting this function? See our previous slide. All I'm doing is plugging in 1/4 for x. But in case you're confused, I'll write down the slide. Now we can actually get into our integration. So this is going to be y cubed over 1 minus 1/64 on our bounds of 1/2 to 1. This will equal 1 over 1 minus 1/64 multiplied by the quantity 1 minus 1/8. This will equal 64 over 63 multiplied by 7/8, which will equal 8/9. So the answer to our question, to find the probability that the proportion of spectrum shift is more than 1/2 given that the temperature is increased by 1/4 of a unit, is 8/9. Wow, that was quite a bit of work. Let's keep going and look at another example. We are now being asked to consider the joint density function f of x comma y equals x plus 3xy squared all over 4 on the bounds from 0 less than x less than 2 and 0 less than y less than 1. We'll let it be 0 otherwise. We'd now like to find g of x, our marginal distribution. So as we are trying to find g of x, remember that means we are going to need to integrate over y. So this will be integral from 0 to 1 of x plus 3xy squared all over 4 dy. I'm going to take a moment, split this up into two fractions just because I think it looks neater. So we'll have x over 4 plus 3xy squared over 4 dy. Now we'll begin to integrate. So we'll have xy over 4 plus 3xy cubed over, whoops, nope, I'm going to take that back because that would be over 12, and I'm going to simplify it further and keep a common denominator of 4. And then you'll need to plug in from 0 to 1, so this will be x over 4 plus x over 4, which will equal x over 2 on the bounds of 0 less than x less than 2. Very, very good. Now, let's do something we haven't done so far and do the marginal distribution h of y. So for h of y, this time we get to integrate over x. So we'll integrate from 0 to 2, x over 4 plus 3xy squared over 4 dx. Now let's integrate. This will be x squared over 8 plus 3x squared y squared over 8 from 0 to 2. This will equal 1/2 plus 3/2 y squared on the bounds from 0 less than y less than 1. Very good. Now let's see if we can't use our marginal distributions to find some conditional events. So let's find f of x given y. So f of x given y equals f of x comma y over h of y. Thanks to our previous work, this is really just a matter of plugging in and simplifying. So this will be x plus 3xy squared all over 4 over our h of y, which we found in slide 34, which is 1/2 plus 3/2 y squared. Simplify, we can get this to be x over, let me think about this. Yes. X multiplied by the quantity 1 plus 3y squared over 4 multiplied by 1/2 multiplied by the quantity 1 plus 3y squared. Crossing out, this will equal x over 2. So, for f of x given y, that would be equal to x over 2 for 0 less than x less than 2. Whew, very good. Let's keep going. Still have 2 more things I'd like to take a look at. All right, probability. So let us find the probability of 1/4 less than x less than 1/2 given that y equals 1/3. So this is not too bad. We will integrate from 1/4 to 1/2, and using our function from above, we were going to use our function f of x given that y equals 1/3 dx. Plugging in, this will be 1/4 to 1/2. Remember, f of x given y is x over 2. And remember, since this doesn't depend on y, this makes this problem a lot easier. So this will be x squared over 4 from 1/4 to 1/2, which will equal 1/16 minus 1/64. Just to get us a common denominator, 4/64 minus 1/64, and we will get a final answer of 3/64. Excellent. All right, very good. Now, let's take a look at let's take a look at something a little bit different, but it'll help us on our 5th objective. We would like to show that f of x comma y equals g of x multiplied by h of y. So if we recall, f of x comma y equaled x plus 3xy squared over 4, and our g of x was, let's double check, g of x was x over 2, and then h of y. 1/2 plus 3/2 y squared. All right, very good. So let's take a moment. If we simplify, we can see that this will be equal to x plus 3x y squared over 4. So therefore, we have successfully shown, and not too difficult either, that h of x comma y equals g of x times h of y. Very good. But why did I ask you to do this? Well, as I alluded to, this has something to do with our 5th objective, to define statistical independence of random variables x and y. So, if f of x given y does not depend on y, then f of x given y equals g of x, and f of x comma y equals g of x multiplied by h of y. So really what we did, and our last example problem, was prove the independence of f of x given y. Well, or I should say at least partially. We showed the first part. So for 2 random variables, x and y, with joint density f of x comma y and marginal distributions g of x and f of y respectively, are statistically independent if and only if f of x comma y equals g of x multiplied by g of y for all x comma y in their range, So in other words, psych, we did show that we have statistical independence. Let's take a look at an example 8. Don't worry, we only have 2 more examples left, 8 and 9. So let us suppose that x and y have the following joint distribution. Okay, taking a look at our chart, we have our f of x and f of y. Y has the values 1, 3, and 5. X can have the values of 2 and 4. And in the center of our table, we have our probabilities. So, first, if we are asked to find g of x equal, again, to the summation over y of f of x comma y, then we can see that g of 2 equals 0.1 plus 0.2 plus 0.1, which equals 0.4. And g of 4 equals 0.15, 0.3 plus 0.15, which equals 0.6. Now to find h of y, which we calculate by doing the summation over x of f of x comma y, we can see that h of 1 is going to be 0.1 plus 0.15, which is going to be 0.25. H of 3 will be 0.2 plus 0.3, which will equal 0.5. And last but not least, h of 5 will be 0.1 plus 0.15, which will equal 0.25. Very good. So, now that we have our marginal distributions that we calculated on the previous slide here, we can now calculate for independence. So, for example, if we wanted to find, or rather to see if f of 2 comma 1 was independent, we would see if it equals g of 2 multiplied by h of 1. So, h of 2 comma 1 equals 0.1. G of 2 is 0.6. H of 1 is 0.25. Well, let's take a second to multiply. 0.6 multiplied by 0.25 equals 0.15. Uh-oh, that means either I made an error or it's not independent. Let's take a moment and double check our work. So, once again, f of 2 comma 1 is equal to 0.1. We can agree on that. Next, let's check. Oops, I see my problem. I had us multiplying 0.4, I had us multiply, or at least in my calculator. Ooh, I really messed up. All right, rewind. Okay, so from our previous slide, we calculated the following marginal probabilities. Whoop, sliding all over the place here. Okay, so continuing on, we can see that the marginal distributions that we calculated from the previous slide are located right here. Now let's test for some statistical independence. Let's start off with f of 2 comma 1. So from our table, we know that f of 2 comma 1 equals 0.1. Now, if it's statistically independent, then g of 2 multiplied by h of 1 will also have to equal 0.1. Let's double check. G of 2 equals 0.4, h of 1 equals 0.25, multiplied together, and yes indeed, we have 0.1. So we have independence. Let's do another check. So if we have h of 4 comma 5 equal, or rather, whoop, rewind. So let's check. H of 4 comma 5 is going to be 0.15. Let's check with our marginal distributions. So this would be g of 4 multiplied by h of 5. G of 4 is 0.6, h of 5 is 0.25, multiplied together, and we have 0.15. Works out. So h of x comma y equals g of x multiplied by h of y for all pairs x comma y. We could keep checking, but that seems unnecessary. But by all means, if you want to do it, go right ahead. But instead, I'd like to take a look at our final example. So we have the joint density function of random variables x and y is f of x comma y equals 2 for 0 less than x less than or equal to y less than 1. Let it be 0 otherwise. So if we wish to calculate our marginal distributions, g of x would equal the integral from x to 1 of 2 dy, which would equal 2y from x to 1, which would equal 2 minus 2x for x belonging to the bounds from 0 to 1. H of y, we would integrate over x, would be the integral from 0 to y, 2 dx, which would equal 2x from 0 to y, which would equal 2y for y belonging to the bounds from 0 to 1. If we were to multiply, we could see that f of x comma y, which would be equal to 2, would not equal the quantity of 2 minus 2x multiplied by 2y. Therefore, x and y are not statistically independent. But just for fun, let's take a second and find the probability of 1/4 less than x less than 1/2 given y equals 3/4. Because never hurts to practice too much. So for us, we know that f of x given y is going to equal f of x comma y over h of y. We know f of x comma y is 2 and h of y is 2y from our previous slide. This means that we will have f of x given y as 1 over y for 0 less than x less than y. So in order to find our probability function, we would need to integrate from 1/4 to 1/2 of our f of x given y value of 1 over y dx, which would equal the integral of 1/4 to 1/2 4/3 dx, which would equal 4/3 x from 1/4 to 1/2, which would be 2/3 minus 1/3, which would be equivalent to 1/3. Very good. Okay, so now finally we are at the end of this section. Let's do a quick summary. So, one of the things we learned was that joint density functions allow us to consider multiple random variables simultaneously. Second, we learned that conditional probability densities allow us to find probabilities for one random variable given a fixed value of another random variable. And finally, we learned about statistical independence of random variables. Remember our rule, f of x comma y equals g of x multiplied by h of y. Okay, that's it. Have a great night. Don't forget to do your homework and email me if you have any questions.